Hey everybody! Today we're going to be analyzing functions with restricted domains. What do we mean by restricted domains? Well, we mean functions in which the domain is not allowed to be all real numbers, and we'll dive a little deeper into that as we go along. But why do we need to do something like this? It's because the goal of algebra is, of course, to be able to tackle any type of algebraic equation that comes our way, and every now and then we have algebraic equations that arise from functions with restricted domains. And so we will solve these equations and we will end up with a solution that doesn't quite work. We call the solution an extraneous solution. Extraneous, like extraneous. A solution that solves my equation but doesn't satisfy my equation. And why does that happen is because we just happen to get a solution that is not within my domain. So of course we need to be familiar with the domain of a function. So I have the definition over here. The domain is the set of all inputs of a function f of x, also known as the set of all x values that are allowed to be plugged into f of x. I like to phrase it as the set of all x values that can go into our function because, well, when we're dealing with the function f of x, x is the input, and so the set of all x values that are allowed to go into our function represent the domain of this function. We're not just going to be exploring the domain, we're also going to be exploring the range is kind of like the domain, but in terms of the y-axis, it's the set of all outputs of our function f of x. Let's take a second to dive into the three most common functions that we may deal with in algebra that have restricted domains. These functions are the rational function, the logarithmic function, and the square root function. These are our most famously known restricted domain functions. And so I have a graph of each parent function. Here, I'm going to take it upon myself to also write the equation of the parent function. The parent rational function is the equation y equals 1 over x. That x in the denominator is what gives us this interesting shape that we have here. We'll talk a little bit more about why that function has the shape it does after we go over the other two functions. Now we have the logarithmic function. The parent logarithmic function takes the form y equals log of x. The fact that there's only certain values that can go into a logarithm is what makes this function have its restricted values that we'll talk about in a second. The last one that we're going to explore today is the square root function. The parent square root function takes the equation y equals the square root of x. And so now let's dive a little bit more into why these functions are restricted. It's all about the behavior of the type of equation that we're dealing with. Look at this function here, a rational function. Every rational function takes the form of a fraction, and we have to think like, what kind of things are not allowed? What kind of things are restricted when we're dealing with fractions? The only thing that comes to my mind is for us to divide by 0. We are not allowed to have a 0 in the denominator of our fraction. Whenever that happens, we result in something that's undefined. And so that's actually where this little gap that you see here between the two pieces of my function, it's perfectly lined up along where x would be equal to 0, aka the y-axis. It has an invisible boundary here that we can't see. Some of you may or may not have already heard of this. It's called an asymptote. An asymptote is like a boundary, kind of like a wall that I approach. I get closer and closer and closer to this boundary, but I never actually reach it. And why can't I reach it? Well, because if I actually reach the y-axis, then that'll mean that x is 0. And when x is 0, I have 0 in the denominator, and I'm not allowed to have 0 in the denominator. And so the restrictions that would arise for this particular function's domain is that we're not allowed to have 0 in the denominator, so can't divide by 0. We might also call that the divide by 0 error. But ultimately, we need to know that we can't have 0 in the denominator. Denominator cannot equal 0. Cannot equal that, because when that happens, we result in something that does not exist, and it creates this gap in our function. Our function has two pieces. It starts over here, but then it has to jump over the y-axis, because that's where x is 0, and it finishes over there. Now we talked about how the domain consists of all of the x values that are allowed to go into our function. And so if we think about this restriction, this is literally the amount. This literally represents the x values that are not allowed to go into the function. And so if I'm trying to figure out the domain, I know that the domain of this function here is everything except for when x is equal to 0. Because when x is equal to 0, we have an undefined part of our function. And so we can say that the domain, I'll put D for domain, is just pretty much everything except for 0. I can write it as simple as that, saying x is not 0, which thus implies that x is everything except for 0, which is entirely true. Or we can write it in a more complex way. Maybe I want to write it in terms of an inequality. I can say that x is greater than 0 or x is less than 0, something like that. Maybe we want to be a little bit more advanced and we want to write it in interval notation, which is my preferred notation. In that case, I will say, well, this function starts coming all the way from the left, and it takes a little pause when it gets here. So as far left as I can be, that's negative infinity. And it goes all the way until I get to 0. It jumps over 0, so I have to union that with the other chunk on the right side of 0 that starts back up at 0 all the way into infinity. It goes on forever and ever and ever. There's multiple ways to write this, of course. Let's go and explore the logarithmic function for a second. So now we're talking about the logarithmic function. What is not allowed in a logarithmic function? You may already know. You may already have some ideas because maybe you've experimented around with plugging numbers into the log function on your calculator, and you see that sometimes it'll output an error message. So when is that happening and why is that happening? That arises our next domain restriction for this function. So if we examine the graph that we have here of our logarithmic function, we can see that the graph only exists on this side of the y-axis. It doesn't exist on this left side. And what's over there on the left side of the y-axis? Well, that's all of the negative x values, because that's where the x-axis is negative. And so what is that telling me? It's telling me that if I'm going to plug an x value into my logarithmic function, it has to be a positive x value. No negatives can go into logarithms. And we can verify that by putting a negative number into a log in our calculator, and poof, out we'll see the error message that I was referring to. Another thing, though, that is also not allowed to go into a logarithmic function, if you notice that this function also approaches a boundary that's invisible, but it's there. It also has an asymptote here at 0. And why is that? Is because another thing that is not allowed to be plugged into the logarithmic function is also a 0. So there's two restrictions that we have here. We're not allowed to plug negatives in, and we cannot plug 0 in. Okay. And so I'm going to actually write the restrictions down here. For our rational function, we said the denominator can never equal 0. So whatever x value makes that happen, we need to make sure that it doesn't end up in our domain. That x value may just be the number 0, but it can really be any x value. We know that x is a variable, so it varies. There's varying values for each function that will make the function undefined, yeah. As we see, the parent function is undefined at when x is 0, but other functions can be undefined in other places, yeah. And so we said our restriction for this one is that the input can never be 0 or a negative number. And so how would we define the domain of this function here? Well, it's not allowed to be negative. It's not allowed to be 0. That means it can only be things that are positive. So I can say that this is everything greater than 0. I can write it like that, but I'm going to go and write it again in my favorite notation, interval notation. I see that this function starts at 0, but it doesn't actually ever reach 0. So I'm going to use an open parenthesis instead of a closed bracket, and it goes all the way to the right. It never stops going to the right ever and ever and ever. And so we know that it approaches infinity, and that's our domain. Pretty simple. As for the square root function, we have to think of the anatomy of the square root operation. So what things aren't allowed to go into square roots? I hope that you said negative numbers. We can never take the square root of a negative number, at least not in the real world, we cannot. And so when we're dealing with the square root function, what am I not allowed to have? Well, I am not allowed to plug in any negative numbers. So what does that mean I am allowed to have? Well, I'm allowed to have positive numbers. Nice. I'm also allowed to be 0. As you see, it actually touches the y-axis this time, unlike these other two functions that we explored. They never touch the y-axis, so x could never be 0, but this function x is allowed to be 0 because we have a nice point right on the y-axis. And so the domain of this function is pretty much everything greater than or equal to 0. So I can write it like this, which would be different than the domain we had over here that was just x greater than 0. But again, we're going to write it in interval notation. This time I am allowed to be 0, so I'm going to use a closed bracket. And I start at 0 and go all the way to infinity. And of course, I never reach there. It's impossible to reach infinity. But let's take a second now and just explore the range of each of these functions in CAM. So the range, I think the easiest way to think of it is to just rotate your graph so many degrees in one direction and then just kind of imagine the domain of that new version of the graph. That of course sounded extremely confusing what I just said, so let's just explore it the regular way we would typically do that. So in terms of the range, what are we looking at? We're now looking at the span of which the function ranges, but this time in terms of the y-axis. The x-axis, I was looking for how far left does this function go and how far right does it go. Now that I'm looking for the range, I'm looking for how low does this function go and how high up does it go. And so imagining this function, I see that it's going low, 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 low. It never stops going low. It goes as low as negative infinity, as we like to say. And then it goes up. It goes up, 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 up. We see that it's going up, but it doesn't just go up forever. It actually goes up with a restriction. It also is not allowed to cross the x-axis, which is just a coincidence, not necessarily a coincidence, but it is coincidental how it happens to also be on the x-axis. This here is called a horizontal asymptote. The other one was called a vertical asymptote. But being that I can't cross that asymptote, my function is going to come up from negative infinity. It's going to get as high as it can, and we know that that's 0, at least for this part of the function. And then we jump over to the second piece of the function. To do the jump, I need a union, a U, to unite the pieces together. And then I start back at 0, of course, not actually at 0, but right after it. And I go all the way into positive infinity because it goes on and 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 on forever in the upward direction. Sorry about that. And so yeah, that would be the range of that. Let's imagine the range of this. So I always like to ask myself, how low does it go and how high does it get? So this goes pretty low. It never stops going low. And so I know that it'll go as low as negative infinity. And then even though this may look that it stabilizes out at some line, it absolutely does not. It actually, believe it or not, goes up, 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 and keeps going up nonstop forever and ever. And so I know the range is negative infinity to positive infinity. It can be any value. We can also call this all real numbers if you're someone who likes using words rather than fancy math symbols. Last but not least, the range of this function, and then also the restriction, because I forgot to write that. The range of this function, as we see, how low can it go? It can go as low as 0, and it touches 0, so I'm going to use the closed bracket, and it goes up, 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 just like the logarithmic function with no restricted height value, all the way to infinity. And that's the range of that. What did we say our restriction was for this one? We said that the input can never be negative. Well, it can be 0, my bad. Be negative. That's the only thing not allowed if we are in the real world dealing with square root functions, yeah. And so again, just another quick reminder, why does any of this matter? Is because if you happen to solve one of these 3 types of equations, you have to always, always, always check your work. If you do not check your work, then you may just have gotten an extraneous solution. And if you did get an extraneous solution, well, then you got the wrong answer. And so it's very important that when we're dealing with these three particular types of functions, to always check our work at the end to make sure that the solution that we actually got is in our domain. So making sure that it's not extraneous.